Hello, everyone. So, this is our topic for today. Hopefully, you'll listen and hopefully, you'll also learn something from it. So, with that, let's now officially begin. There was a period of time wherein paradigms didn't exist in the nature of dealing with scientific problems. This directionless research led to various criteria to evaluate theories about basic scientific problems. But when a paradigm was established, it created a consensus between sciences for normal science to work within. But before we explain further, let us introduce Thomas S. Kuhn. He was an American historian of science, and in 1962, one of his influential works of history and philosophy, entitled The Structure of Scientific Revolutions, was published. The book tackles the episodes in history in which are known as scientific revolutions, in which this period tackles our scientific knowledge of the way our universe works, is disproved, and replaced by another grasp of knowledge. It also consists of a history of long periods of stagnancy that marks occasional revolutions.
First up, Chapter 4, Normal Science as Puzzle Games. You might ask, what is normal science? Why is it being compared to puzzle games? Well, we are here to answer your questions. Normal science operates within a paradigm. It is not about discovering new phenomena but solving puzzles that the paradigm defines to understand the world. Scientists are expected to find solutions that fit within the existing rules of the paradigm. This extends the precision and scope within which it has been ordered. As stated by Kuhn, it limits both the nature of acceptable solutions and the steps they are to be obtained. This just means that normal science follows the agreed frameworks of a paradigm to serve as a guide for scientists whenever they are conducting research or experiments. Before we hop on to answer the question, why is normal science being compared to puzzle games? Let's take a quick detour and differentiate normal science and social science. Let's start with social science. Social science is too complicated for a paradigm, are not puzzles because they are not solvable, and they are too problematic as it takes too much time. Meanwhile, normal science is problems or are problems in the field that have solution and that are fit for a paradigm. They are measurable and solvable, hence normal science as puzzle solving. Now, going back, why is it being compared to puzzle games? Well, normal science progresses rapidly as practitioners focus on the problems that are puzzles and are solvable by their skills. The problem in normal science is a puzzle that is solvable with a solution. Discoveries that don't fit the paradigm are often ignored. These puzzles refer to everyday problems within a scientific discipline that scientists need to work to solve using a given paradigm. Now, a puzzle is considered legitimate only if 1. It can be solved using known methods. 2. It contributes to a normal paradigms, it contributes to a paradigm's improvement. And number 3, it conveys that anything outside of the paradigm will mean nothing as they don't fit it. Additionally, Kuhn compares scientific work to solving a jigsaw puzzle. The pieces must fit the picture. A puzzle is a category of problems that can be a test that to a talent or skill in solution. Next, the puzzler is a scientist that has the conviction to solve the puzzle. Finally, the puzzle itself has all these pieces that have their own place and shapes in order to solve a puzzle that has no holes like the rules in scientific problems in order to come up with the expected outcome. Therefore, both jigsaw puzzle and normal science have rules or a paradigm that needs to be followed in order to achieve the expected outcome. Another thing, development of new instruments is often driven by the need to solve for paradigm-defined puzzles. Instruments are not valued for their novelty, but their ability to produce expected outcomes or results more precisely. Overall, a solution is not judged by how well it conforms to a paradigm's expectation. Failure to solve a puzzle is seen as a failure of a scientist and not a paradigm. Continuous failure may eventually lead to a scientist questioning the paradigm. According to Kuhn, normal science is a highly determined activity, but it does not need to be entirely determined by the rules. That is why he introduced shared paradigms rather than shared rules, assumptions, and points of view as the source of coherence for normal research traditions. Because of a paradigm, the important ones are those that are solvable puzzles and those that are fit for a paradigm.
Hi, did you miss me? Up next, chapter 5, the priority of paradigms. The major theme of this chapter is that rules are derived from paradigms. As per Kuhn, paradigms could determine normal science without the intervention of discoverable rules. Kuhn argues that if one's experience had been all like his own, that person will have found the search for rules both more difficult and less satisfying than the search for paradigms. Normal science can be determined in part by the direct inspection of paradigms, a process that works with rules and assumptions but does not depend upon the formulation. To put this in context, there was a pre paradigm era in normal science that universal rules cannot direct scientific problems across different fields of science. The debates are more frequent during these times. Going back, paradigms, a concrete paradigm, is a process that is frequently aided but independent on the formulation of rules and assumptions. It is believed that credible research is composed of a paradigm. It guides the problem into a narrow solution because paradigms can operate without consensus or even an attempt at rationalization. Therefore, a lack of standard interpretation of an agreed reduction to rules will not prevent a diagram from guiding research. Moreover, the scientific community shares paradigms to discover isolable elements. The scientists search for a paradigm helps solve the problem as the community has their shared belief. The shared belief of the community of scientists aids the search for a paradigm to contribute to problem solving. There are four reasons that for paradigms direct normal science without rules. There was a difficulty in discovering rules to guide specific normal scientific traditions. This is the same concern of Wittgenstein in describing the commonality of games. He cannot strictly pinpoint their definition, as Kuhn points out that universal rules will not apply to all scientific traditions and fields. The nature of scientific education is rooted from practice and application. The practice of scientists is to refer to prior work of concepts, laws, and theories in abstract. And when there is a new theory, they must demonstrate its application to a natural phenomenon to be a candidate for acceptance to go over, saying that it is only an abstract of definition. Paradigms guide research, though, through direct modeling with the help of abstracted rules. Normal science can proceed without rules as long as the relevant scientific community adamantly accepts that it achieve problem solutions. A paradigm creates coherence in the diverse fields of normal science. Because of the diversity of scientific fields, a paradigm is easier to understand than explicit rules because these limit it to a broad scientific group, unlike a paradigm that could educate a widely separated and different scientific field.
Moving on to Chapter 6, Anomaly and the Emergence of Scientific Discoveries. Would you believe that the scientists that we have encountered have had their fair share of anomalies? Well, In contrast to the negative connotation of the word anomaly, in normal science, anomalies are an important part of progress. A discovery in normal science is not a discovery without the awareness of it being an anomaly first. Anomaly occurs when there is an odd behavior within a paradigm. This exploration continues until the anomaly is expected with the adjustment of the paradigm theory, but also not until scientists have had a different perspective of the nature of the mind initially is only expected in our usual experience, even under circumstances where anomaly is later to be observed. Further contact, however, does not result in awareness of something wrong or does not relate to the effect to something that has gone wrong before. Discovery. Discovery is a process and must take time. Only when all the relevant conceptual categories are provided ahead of time, in which case of phenomenon would not be a new sort, can discover that and discover what occurs effortlessly together and in an instant. We could put this into perspective. For example, the discovery of oxygen. Anomalies played an important role in the discovery of oxygen. It started with the anomaly of Carl Wilhelm Scheele. He obtained a relatively pure sample of gas, although his discovery is not a part of the known paradigm, but the following are. Joseph Priestley collected the gas released by a heated Bragg oxide of mercury, and in 1774 he produced nitrous oxide that he described as common air with less than its usual quantity of phlogiston. In 1775, because of the phlogiston theory, he thought that oxygen was just an ordinary gas. The anomaly was formed because he was restricted to an old paradigm. Then came Antoine Lavoisier. His work is a result of hints from Priestley. In 1777, he identified a substance as oxygen. This new paradigm was based on his doubt on Lavoisier's phlogiston theory, therefore marks a scientific revolution and an effective paradigm change. Since the aim of normal science is not producing novelties of fact or theory, due to the repeated discovery of phenomena and invention of theories, it is claimed that the scientific enterprise has developed a new technique for producing the fundamental novelties of fact and theory. After these become one with science, the specific field is its new kind.
Hi. And finally, chapter 10, Revolutions as Changes of Worldviews. This for sure is an interesting topic as this tackles how scientific revolutions changes the world's view. Well, as you all know, paradigms are the reason why normal science operates. That is why when paradigms change, the world changes with them. When led by a new paradigm, scientists adopt new instruments and look in new places. During revolutions, scientists see new and different things when looking with familiar instruments in places they have looked before. Of course, as paradigms change, it also affects perception. That being said, if there was no external standard with respect to which a switch of vision could be demonstrated, the scientists would have no conclusion about the alternate perception of possibilities that could be drawn from the duck rabbit experiment. Also, if perceptual switches accompany paradigm changes, we may not expect scientists to at least address these changes directly. The world changes when someone interprets and finds something new within the given paradigm. Some examples include Galileo's interpreted observations of the pendulum, Aristotle's observations on falling stone, Muschenbroek's observation on a charge-filled bottle, Franklin's observation on a condenser. An example of scientific revolution changing accepted facts is when John Dalton, a new paradigm, made chemists come to live in a world where reactions behave quite differently from the way they had before. And that's it. We have covered chapter 4, 5, and 6, and 10 of Thomas Kuhn's The Structure of Scientific Revolutions. Kuhn truly was a great figure in philosophy and in the history of science. He fundamentally changed how philosophers, historians, and scientists view the progression of scientific knowledge, moving away from purely logical models towards a more historical and sociological approach.